I've been following some of the videos analyzing the UFO or UAP videos released by the US Navy. One specific series of videos that I've been following is this one between Mick West and a former F-16 pilot called Chris Lato. In these videos, Chris Lato criticizes some of Mick West's earlier analysis, and Mick responds. Then there's a bit of back and forth discussion. Chris's style is a bit theatrical in places and contrasts with Mick's more deadpan delivery, so it's an interesting debate to follow. The videos cover quite a few topics and jump around a bit, so some things are skipped over and there are a few parts that are confusing or have misconceptions. I thought it would be useful to clarify some aspects for people who might not be familiar with some of the flight dynamics that they are discussing. In this video, I'm going to focus on one of the main topics in the videos, the turn rate discussion and what this means for the Gimbal UAP range. I'm not going to do a full analysis here, but my objectives in this video are just to derive and explain the very simple maths behind the turn rate, and then use that to comment on Chris and Mick's analysis, and correct or clarify a few misconceptions in the videos. I think there are issues with both sets of analysis, and I'll explain what they are. In Chris Lato's video, he uses basic trigonometry and turn rate estimates to calculate a set of bearing lines to the UAP and uses those to estimate position and speed. The turn rate calculation is absolutely critical to the argument, and there's some debate between Chris and Mick about what the turn rate is. So first, let's derive the simple equations for turn rate so we can understand who is correct. There are some assumptions we have to be aware of, and I'll mention some of these as we go along. The first assumption is that we have an object that is flying at a constant altitude with a constant speed v. To maintain the altitude, we need a vertical force to balance the weight. I've called it Fv here. Now let's look at this in 3 dimensions, and say we want to fly in a circle, still with altitude constant. In order to fly in a circle, we need to create a horizontal force to generate the acceleration that will cause the object to turn in a circle. I've called that force Fh here. These 2 forces are all we need to fly in a circle at constant height. Now let's look at how a typical aircraft generates these forces, which is important for how Chris and Mick derive turn rate from the gimbal video. An aircraft with a planar wing generates the majority of the force in a direction normal to the wing. So for straight and level flight, the wings are level and the resultant force is vertical, balancing the weight. In order to generate turning flight, the aircraft is banked. The force generated by the wing is still normal to the wing, so in order to create the vertical force necessary to balance weight, the force F here needs to be increased. In this condition, the aircraft generates the necessary Fv plus a horizontal Fh component and performs a turn. If we bank to a higher angle, the force F needs to be increased further to maintain the vertical component needed, and this means Fh is also increased and we turn quicker. It is this relationship between bank angle and turn rate that Chris and Mick are using to deduce the turn rate in the gimbal video. If we think about the accelerations caused by these components Fv and Fh, we can see that Fv needs to generate 1g of acceleration to balance the acceleration due to gravity, and then by basic trigonometry, Fh will generate tan theta g of acceleration towards the center of our turn. Now we can use the simple equations of circular motion to derive turn radius and turn rate. In circular motion, the acceleration is v squared over r, or r omega squared, where r is the radius and omega is the turn rate in radians per second. We just showed that our acceleration is g tan theta, so we can deduce that the radius of the turn r is v squared over g tan theta, and the turn rate is simply v over r. Notice that mass doesn't figure in these equations. For a given bank angle in a steady level turn, the radius of turn and turn rate are fixed and independent of mass. Chris doesn't show the detailed calculations, but he is using these equations to draw his sketch. Mick West uses a rate of turn chart for the F-18 that we can show is using the same equations, and then puts the turn rate into an online tool called GeoGebra. Just a quick aside here. Here is the chart that Mick uses. It's taken from the US Navy F-18 flight manual. It shows turn rate for different bank angles as a function of speed on a log-log scale. It's actually just a plot of the equations we just derived, but surprisingly the chart has some mistakes in it. If we look at this section of the chart, we can see a couple of issues. First, looking at the scale between 1 and 10. On the log scale, this is 1, 2, 3, 4, etc. But when you get to 4, you can see the line is in the wrong place. On a log scale, each subsequent interval should be smaller than the previous one, but the interval between 3 and 4 is smaller than between 4 and 5, so it's clearly wrong. To check this, I overplotted the results from the equations we derived earlier, and you can see the error. Most lines are a good fit, but there's some error in the region where the scale is in the wrong place. Unfortunately, this error is in the region Mick West used in his video, which was a speed of about 350 knots and 30-degree bank angle. There's also another error on the chart where the load factor is listed as 1.1 G, but it should be 1.01 G, but this doesn't affect this calculation. This chart was probably hand-drawn and has errors, but I'm slightly surprised that this hasn't been spotted and corrected over the life of the aircraft. If we repeat Mick's calculation using our equations instead of the chart, we get a slightly different result, 1.8 degrees per second instead of his estimated 1.7. That's about a 5 or 6% error. So we've established the basic equations for turn rate that both Chris Lato and Mick West are using. I don't plan to analyze the gimbal video in detail, but I will make some comments on Chris and Mick's videos. Chris's approach is obviously based on his training as a pilot, where it's necessary to make quick calculations, and accuracy is slightly sacrificed. It's better to have a rough answer quickly than a more accurate answer that takes a long time to derive. Even so, Chris's calculations are not very accurate, and he seems to overestimate the turn rate in some places. In this application, small inaccuracies can make a big difference to the conclusion. One important point to note that he's trying to estimate the position of the target, not from the intersection of the bearing lines, but by assuming the target is moving at a fixed speed and finding a position and angle of the target trajectory that gives equal distance between the bearing lines, as this would mean the target is moving at a constant speed. There's no real justification given for assuming constant speed. This technique is highly sensitive to errors in this example. His three bearing lines almost intersect at a point, so as he points out, the target could be at almost any range depending on its speed. He rules out a longer range by saying that the target would have to be going supersonic, but there are many aircraft that can go supersonic, and presumably alien aircraft might be able to do that too. Even without considering the inaccuracy in his bearing lines, his range result is not convincing. In his second video, he also mistakenly says that mass affects turn rate, and heavier jets require more G to maintain the same altitude. He uses this to justify using a higher G and hence derives a higher turn rate. This is not correct. The equation we derived and the F-18 chart both show that aircraft mass is not important. His bearing lines are therefore not accurate, so his analysis of target position, speed and direction is questionable. Mick's turn rate calculations are probably more accurate, even allowing for the error in the chart he uses. He focuses on disputing Chris's turn rate and then estimating position based on the intersection of the bearing lines. This is a slightly different approach to Chris, as he is effectively assuming, again without justification, that the target is stationary, which seems unlikely. In fact, his hypothesis that the target is a conventional aircraft means it almost certainly cannot be stationary, so there's a contradiction in his argument. He seems to be saying that if the bearing lines become parallel, that means the target is far away. But this is not true. If the target is moving, the bearing lines could be parallel or even diverging, and the target could still be close. He also says in the description of his video that the intersection shown is a likely minimum distance, but with no justification. If the target is moving, the intersection really has no physical meaning, and the target could be further away or closer than the intersection point, depending on its speed and direction. It could also be turning. My conclusion is that neither Chris nor Mick have provided a convincing analysis to determine the position of the target. For a convincing analysis, sensitivity to errors needs to be considered, as well as the possibility that the target is moving and might be accelerating or turning. The obvious question that I haven't seen answered is what happened next. The F-18 has turned towards the target, so there should be some more information available in the seconds after the video stops. Does the target fly away? Does it disappear? Does the F-18 close on the target? It seems that there should be more information available, but it's not being released to the public. Unfortunately, from this series of videos, nothing is debunked or de-debunked. Let me know in the comments if you see any problems in my analysis, or if you have any other comments or questions. If you know of any more detailed analysis of the gimbal video, leave me a link in the comments. Otherwise, I may have a go at doing some analysis myself.